Hello, everybody. How's it going? Good to see you all. Oh, everyone's here. Look at this. The whole class. The entire class. I think. You know what? I better check that. Just in case with my attendance thing. Hold on. How y'all doing? Everyone doing okay?
Yeah.
It's good to hear. Where in the world is my email? Oh boy, I have to actually check. Let's look. Let's look. Sorry guys, just doing a little bit of admin here, but we're going to get going and look at vectors today. So if you have something to take notes with, I highly suggest that you get it out. Aha. Aha. There's actually one person who transferred into class who I need to get onto our class here. So give me just a second. Oh boy. I need to find an email. Oh, that's not right. Oh my goodness. We're Physics 1, is that right? I just want to make sure I have the right class notes up in front of me. Sorry, guys. You'll have to amuse yourselves for a moment. While I do some admin. Isn't being online great? Yeah. Okay, hold on just a quick second. Okay, there we go. Oh, my goodness. Sorry about that, guys. Let's do this. Okay. Wonderful. Now, today I wanted to start looking at vectors, sort of the idea of this new mathematical concept. Has anyone ever worked with vectors before?
For like a few minutes in Mr. Grange's class.
Good, that's excellent.
The last thing we did.
Oh, and by the way, I need to mention I am recording myself, just my video, and my sound. I'm not sure if it gets your sound at all, but I know it's not getting any of your videos, so hopefully thumbs up with that. And so just in case, like if there's chat questions or if there's like verbal questions, I'm going to try to repeat them just so on the recording, people who miss class or if anyone wants to go back through, will have kind of a record of that. I'll post this on probably my school YouTube channel, and it'll be up on our classroom as soon as I can get my act together. So I'm going to try, cross your fingers, try to post the recordings of classes as well as any lecture notes that I have and anything else that goes along with it as quickly as I can after lectures. It takes a little bit for me to edit down the video so it's not too long and all that. So you'll see it pop up on Classroom. Okay. Any questions or concerns about that before we get started? All right. Sounds good, you guys. All right. First things first, then. I'm going to use this guy. Little whiteboard I've got, and I've got a little tablet to draw with. The concept of vectors is really central to what physics is as a science, as a discipline, I guess. The most basic sense of it is that a vector is a number, a lot like the numbers we're used to, right? Like 6 or 437, two of the best numbers of all time. Everyone knows. That's a joke. Everyone knows the best number is 4. Anyway, these are just regular numbers, which we would call scalars. And these are just numbers that have a size, but nothing else. They are, maybe 6 apples or 437 meters. These are just measurements of some size of something, at least in physics. Whereas vectors have a size, we call it a magnitude, but it also has a direction. So, for example, let's say 42 steps west is a vector. Or, let's see, come up with another good example that's different than that. 2 meters. Let's do really technical. 113 degrees clockwise from north. That'd be a really technical way to do it. So the vector has the size component, like the magnitude here, like a scalar does, like we're used to, but it also has to include this direction part. So the parts of a vector are 1, magnitude, and 2, direction. And we usually represent them as like an arrow. So for example, if I have my XY coordinate plane and I'm standing here, I can give myself a vector direction to walk in some certain direction, some certain distance. And that's my ending point. And that's how I would draw the vector. Right there. And maybe I'll call this vector v, because, you know, vector starts with v. And there's a special notation that goes along with it. This little kind of half arrow that goes above the v. So I'm going to write that over here, vector notation. So let's say we have a vector. We're going to use the letter v at first. We can use any letter we want. But in order to denote to ourselves and to anyone else reading it that it is a vector, we're going to use this little half arrow over it. I like to use the half arrow. I've seen people use a full arrow, and there's other, you know, in a textbook. I think our textbook does this, but a lot of textbooks will use just a bold letter to make a vector. Some of the really classic physics textbooks just use a really bold letter. I will never do that because I feel like it's really hard to tell. I always use the half arrow for a couple of reasons. One, it's easier to tell that it's a vector. Two, the half arrow is way lazier than drawing a full arrow. And one thing you'll learn about physicists is that if you can be lazy, you're going to do it. The best physicist is the laziest physicist, who still gets the problems done. That's an important point to make. If you never get the problems done, you're not a very good physicist. But if you get everything done in the laziest possible way, that's a good physicist. I guess that's the way people have defined it anyway. So, there we go. There are vectors with a magnitude and a direction. This is going to be really important for, it's kind of a foundational thing for future units when we get into stuff like ballistic motion and like firing things out of a cannon, things like that. Thinking about thing like a velocity as a vector, which it is a vector, is really important. So we're going to try, first thing here in our first little mini unit, we're going to try to make sure we have a really solid foundation on what vectors are and how to do all the math around them. Because I don't know about you, but when I first thought about it, when I first was introduced to this concept of a magnitude and a direction, I was pretty comfortable with adding together, 6 and 437 over there, and I could add 42 and 2, but how do I add west to north? That's quite the question, right? So adding two vectors together, or subtracting them, is what we're going to learn. The biggest thing we're going to learn in this unit, I think. There is also a way to multiply vectors. There's actually several different ways to multiply vectors. We are not going to learn it in this class, but I'm going to mention it just in case you're interested. So let's say we have vectors A and B. You can add A plus B. You can subtract A minus B. And it works a lot like addition and subtraction that we're familiar with. We're going to learn this kind of stuff. Physics 1. And then in Physics 2, we're going to very briefly at the end of the class, we're going to talk about vector multiplication. But there's multiple ways to do it. And I just kind of want to show it to you just in case you decide not to take Physics 2 or you don't have time or something. This here is called the dot product. Whoops. My pen's having some issues. There we go. The dot product is multiplying the two vectors. Let's say we have vector A and B. The dot product is like taking this vector A and projecting it into the direction of B and figuring out how far it goes. So it goes like that far. And it gives us just a scalar. It gives us just a number. Whereas the other way of vector multiplication, the cross product, would take vector A and B and do some weird things to them, and it would get a vector coming out of the page straight into your face that is some weird multiplication of those two. So That, thankfully, we don't need to worry about right now for this entire year, because vector multiplication is kind of ugly. There's actually at least one more way to multiply vectors that I don't even want to get into. Yeah, it's real advanced math. I didn't see it until I was in junior year of college, so I'm not even going to mention it. But if you do decide to take Physics 2 eventually, you'll probably learn these a little bit towards the very end of the course. So just to let you know what's coming. Thankfully, we don't have to worry about that. We're just going to worry about addition and subtraction. So like back to elementary school. Hooray. Only it's like way more complicated than elementary school. And I think today all we're going to do is just start with addition, and that's all we're going to worry about for vectors. And by the way, I wanted to mention too, I am not planning to give any homework until next week, when I can do a video for you introducing this as well. The video will very much be a review of exactly this stuff that we're doing right now, but hopefully organized a little better than my lecture here. Okay, I'm going to section off a new section. Oh god, I'm terrible at the drawings. There we go. Hooray. And by the way, I'm going to, as long as I remember to save it, I'm going to upload this this little drawing document that I've got here for you to see on our classroom as well. Okay, so vector addition. Oh, you know what? Before I really get stuck into vector addition, I want to ask, how are people doing? I seem to have lost someone off of their screen. But are you guys doing okay? Oh, there you are. You're just tired. I get it. It's all right. I get it. This is a lot. We doing okay? We like super tired, sick of being online? Yeah.
Yep. It's already tiring being online, and we're 3 days in.
I know. I'm exhausted already. Let's just take a second to breathe. Just be where we are. Okay. All right. So, adding vectors. There's two ways, or a couple of ways to think. I shouldn't just say two. There's more than two ways to think about it. There's two ways I wanted to approach thinking about it today. But the very first one is kind of a graphical interpretation, not very mathematical, geometrical, I guess. I'm going to draw my XY coordinates here again. Oh, God, that's terrible. I'm just kind of going freehand, and I've never been good at straight lines. You would think... Oh, my God, that was even worse. You know what? Screw it. I don't even need it. Whatever. We're going to go with vectors A and B again. So let's say that this is A. And, I don't know, B can look something like that. And give them the little vector symbols. If I wanted to add A plus B, there's a couple ways to do it. And the graphical way, I think, is the most intuitive. I'm going to start at the origin, x, y, 0, because that's where you start. It's the origin. And then, basically, I'm doing A plus B, so I'm going to think about like myself as a little guy walking along the XY plane, and then I'm going to walk A. So here's my A. I'm going to try to make it as close to this original A I drew. There's A. And then, since I'm adding B to it, I'm also going to walk B once I get to the end of A. I'm going to try to, again, I need to make it as parallel as I can to this B and the same length. And so the vector A plus B, I'm going to call it C, is going from where I started at the origin to where I ended up at the end of B. So basically, I just think about it as walking A as a path, then walking B as a path, and that's my C. And I guess the result is that I've walked these two, I've added them together, but I could have just walked C, which is the result. Is how they add together. And I could do it in any order, right? I could have done this same B with the same length and parallel down to there. There's your B. And I could go A next, parallel and the same length as the original A. And it gets me to the same point, which is kind of nice. It makes a parallelogram, which is pretty cool. You don't need to, do both versions every time. Most of the time I'll just do A, B, and my C. And my C. There we go. And I make a nice triangle, actually. And I promise you, unless you are like me and kind of masochistic, you're going to be really sick of triangles by the time you finish this class. They're going to pop up everywhere because they're super useful. I need a drink of water there. So, I hope you guys... Actually, now's a good time to see just like a little survey. Give me a thumbs up, thumbs down, just on your video. Who has seen trigonometry, like any of it, in math class? I'm seeing mostly thumbs up. If you haven't, that's totally fine. That's really, really fine. Because what we're going to do, a lot of this unit of vectors is like getting our trigonometry skills either back up to speed with where they should be or just up to speed in the first place. So, not to worry. Just good to know who has a background and who doesn't. And honestly, the trig for this course is the simplest, like, most elementary kind of trig you could ever imagine. It is not hard, and nor is it particularly complicated. It's just sine, cosine, tangent, and, the inverse functions of those, basically. There are, I'll show you some trig identities because they're kind of nice and useful, but otherwise, it's not going to get super complicated. There are a ton of trig identities out there that I remember having to memorize them in math class, and I hated it, but I'm going to try to keep it just to the really useful ones. It's like 4 of them, basically. Okay, so we've added vectors A and B, and we realized we can do it forward, A plus B, or B plus A, and it gets us to the same spot, which is kind of nice. There's our vector C that goes from the beginning to the end. And I think this is a really important point for us to review, because it always causes difficulty, I find, when we're doing it every year. When I'm adding 2 vectors together, A and B, my result vector, C, goes from where I started to wherever I ended. And it doesn't even matter where I went in between. I can add up 1,000 vectors in all sorts of arrangements, going back over each other. And my result vector is going to be, this guy here, from where I started to where I ended, no matter how many vectors I added up. And one of the biggest reasons that I start with vectors as a concept in Physics 1 is because when you get into really deep physics, like the most modern, crazy quantum mechanics stuff, at the real heart of it, all it is adding a bunch of vectors. In that case, in like quantum chromodynamics, you're adding like an infinite series of vectors, technically. You're doing calculus. But it really is at the heart of it adding vectors. The most like fundamental way to describe how light actually works, which is mind-blowing, is just adding a whole bunch of vectors. It's kind of crazy. And figuring out how to do that, really. So it's, to me, the mathematical concept of vectors is like the core concept that really defines physics. And that's why we're starting with it. Also, it gives us like a nice gentle introduction to the math before we get into like equations of motion or anything more complicated than that. Okay. So, unfortunately, since we're not in class, we're not physically there, what I usually would have you do is actually, with a tape measure and compasses, make your own vector instructions. Like, for example, maybe my classroom is here, and here's the 9th grade classroom, and then here's chemistry, and a whole science building. It's a big square, whatever. So maybe we start here, and you write down, okay, walk 4 meters, and then you'll write down a compass bearing. I'm trying to remember the classroom. So like, this is north actually in this map, even though it's down here and the way I've drawn it. That's south, east, west. So what you would usually do in class is you'd take your tape measure, you'd walk to whatever point you want to go to, say out in the hallway through my door, and you'd take a compass bearing, and you'd write down in your notebook, like, say, 4 meters at, I don't know, that's pretty much due south, right? Based on the compass I've drawn, so 180 degrees, because north is 0. South is 180. It goes around, I need to like rotate my perspective. It goes around, I think it goes around this way. So east would be 90 and west would be 270. And you'd give a bunch of directions like this, right? Maybe you walk down here and walk out the door of the science building and maybe walk over to the quad and maybe someone else's classroom. And usually I would have you guys hide a box of candy or something for another class to find. And then I would have them hide one for you so you could find it the next day. Unfortunately, we're not on campus, so you'll just have to have some sort of candy treat of your own. And we might try this exercise, depending on when we get back to campus. We might try this anyway, because I think it's really nice to get a sense of, you know, measurements and how vectors work in sort of the physical world. But sadly, we're not there, and we're going to make do. Any questions before I move on to like the more mathematical, formal part of adding vectors? No? Okay. I'm going to do a new page. Okay. Oh, and I want to be cognizant of my time. I have about half an hour left. That's more than enough time for what I want to do today. We'll get out a little early, which I always think is a good thing. Okay, so adding vectors more mathematically. This is where we're going to get into some complicated stuff. And so today is just meant as a really quick, get your feet in the water kind of introduction. I'm not expecting you to be able to do this right away. We're going to work on the math of this. Do not worry. It's going to be confusing at first because it's a complicated concept. Okay, I'm going to be more formal now. Since I need to do math with it, I need to be really formal about my definitions of my vectors. So again, I'm going to use A and B. I think A was like this. And vector B was, I think I drew it like that. Okay, so we're going to define first the magnitude, or the size of the vector. I don't know, what does that look like? It looks like a 3-meter vector to me, just because no particular reason. And B, I don't know, let's say that's like 2 meters. It's a little bit less. I'm going to draw a dotted line here just to separate. I'm going to do a whole table if I can actually draw anything. Okay, and then direction. This is the tricky one. So, by default in physics, we actually start measuring direction angles from this positive x-axis, plus x, so this direction going out right. We start there, that's our 0, and we go counterclockwise around this direction. Or in B's case, all the way around this direction. I know what you're thinking, well, why don't you just measure this smaller angle? Nope, we want the big one. And the reason for that is we want some standardized way of referring to angles that anyone looking at your measurement can always understand. So again, I'm going to say this probably 1,000 times. You don't have to have it memorized just yet, but if you do, I'd be super thrilled. We start at the positive x-axis, which is the one that goes out to the right, and we measure from there, that's 0, around counterclockwise. So towards the positive y-axis, technically. So what does that angle look like to anybody? Anyone have an idea? That's like a 50 degrees or something, maybe?
Sure.
Yeah. And this one's bigger. This one goes 90, 180, 270, and then what is that? It's like, let's just call it 300. You know, we don't have to be super precise with this. 300 degrees. Okay. So, we've like been really precise now about how we're measuring these vectors and what the vectors are. We're not just drawing some random arrows. Yeah. And I guess I should make the point too that I can draw this vector B anywhere I want, right? So let's say I have this universal coordinate system. I have a big X and Y axis out here somewhere. So X and Y. Vector B is 2 meters long and it goes in a direction of 300 degrees. I could draw that here at the origin like I did in this original picture, but I could draw it anywhere. I could start it here, and as long as it's 2 meters, and at 300 degrees, that's still vector B. I'm just measuring the angle from some sort of imaginary x-axis that's parallel to this original one, right? I'm measuring that 300 degrees there. So I could draw a vector B as many times and anywhere I want. They're always going to be the same size and parallel in all the quadrants, right? They move all over the place. And you know, same for any other vector, vector A. They're not fixed to the origin. Although when you're doing vector math, like adding up A and B, it's always a good idea to start at the origin unless someone tells you otherwise. You know, one of those scenarios might be, say, for example, a test question that I once gave was, you're here at your origin and there's a like an injured hiker over here with some vector directions to them. What are the, and you know, or the injured hiker, maybe someone's lost, they have a radio. What directions do you give them in terms of vectors to get back to where you are, the origin, right? And so you have to imagine, okay, it's me at the origin, but this person's way out here. So you can find that distance still, but you have to think about the angle from their perspective, right? So now the angle is this. Whereas if you were thinking about it from your perspective, it's going the opposite direction, and the angle is there. Just a little bit different. I don't know. Yeah. So being able to shift your perspective is pretty useful. How we doing? How we doing, guys? Thumbs up. Excellent. Excellent, excellent. So we're going to take our vector A. I'm going to draw A out here. Here's my little arrow. One of the cool things about vectors is that it looks like this A is wearing bell bottoms. That's not a cool thing about vectors. It's just a thing. One of the cool things about vectors is that because they can add up, you know, like I showed you on the previous page, I had A plus B equals C. They add up to a third vector. Any one vector you have can be broken down into any pair of other vectors that start where it starts and end where it ends. It's kind of a subtle point. Did I say that well enough for you guys? Is that like too confusing? I'm going to try to move on, and if it's confusing, don't worry, we're going to go over this again. But the fun or the interesting and useful part of this is putting your vectors that you've decided add up to your original vector, making them parallel to your x and y axis is super useful. So what I'm going to call this bottom one here, this long bottom one, I'm going to call it A, vector A subscript x, with a little vector symbol. And similarly, I bet you can guess, this one over here is going to be vector A sub y for y-axis, the one that goes vertical. And they're at a right angle to each other because they're x and y axis. It's super nice. The angle between A sub x and A here, since we've given it, is 50 degrees. That's just what we estimated from looking at our drawing. And we can do the same thing for B. B is like this kind of a guy, and he has a b sub x, and a b sub y. The little arrows go like that. They are perpendicular to each other. So we've made nice little right triangles. And one of the cool things about vectors is that if I want to add a and b, like numerically, what I can really actually do is I can do ax, sorry, I'm going to complete this thought. A plus b equals c. Ax plus bx equals cx. And ay plus by equals cy. This is called componentizing vectors, or adding by components. So the reason you can do this is that the reason you can add ax and bx and they make cx is that they are going in the same direction, or they're at least on the same axis. So maybe ax is like that, and bx is like that. C is just the addition of their two magnitudes. Remember the size of them. So one of the nice things about vectors is that when they're going in the same direction, I'll write this down too, when vectors go in the same direction, they add just like scalars, so like regular numbers we know. Scalars being normal numbers that we're all used to doing math with. So the whole point of breaking down my a into the ax and ay that add up back to a was to have these x and y axes that are always going in the same direction, so that I can also break down b into bx and by and just add up the components really simply. But I'm sure you're asking, well, okay, so I know how long A is. A is 3 meters and B is 2 meters. How do I figure out how long AX and AY are so I can do this simple addition? That, my friends, is trig. So I think most of you said you'd seen some trig before. Does anybody want to volunteer a guess? It's okay if it's wrong. In fact, I should tell you, right now, this moment is the perfect time to be wrong. Not only are you not being graded, I will judge you very kindly and fondly if you get something wrong right now. I'll be very happy because it means you're trying. So, for example, how would I find how long a sub x is using some trigonometry?
Would you use right triangle trig?
Absolutely, you'd use right triangle trig.
You would use, wait, hold on.
If anyone else has it, go ahead and jump in.
So wait. So sine is opposite over
Adjacent.
hypotenuse? Oh yeah.
Is it over adjacent? Cosine is opposite over adjacent. Cosine is adjacent.
No, I thought tangent was opposite over adjacent.
All right, so there's some confusion, and that's totally okay. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent, or otherwise known as sine over cosine. Isn't that neat? Okay. And you know what? We're going to get way more into sine, cosine, and tangent. I have some really, to me anyway, because I'm a super nerd, you'll find this. There's some really cool geometrical interpretations of what sine, cosine, tangent, and all the trig functions are. Maybe next class. I'm not sure exactly when I want to schedule it. Maybe next class I'm going to do this huge diagram for you of all of the actual physical interpretations of what sine, cosine, and tangent and all those are. It's one of my favorite things. It's so nerdy. You're going to be so bored, but I'm going to be so happy. Don't worry. Thankfully, you won't need to know any of it, but I just like it. Oh, whew, lunch is coming back up. Okay, so here we go. Sine of our angle, so sine of 50 degrees, is going to be equal to a sub y over a. And these are the lengths of a sub y and a, which I suppose now is not a great time, but I should introduce the proper notation for this. These are usually vectors, right? Which means they have a size and a direction. All we're interested in this particular calculation is just the magnitude, the size. So down here I'm going to write magnitude of, say, vector A. The way we notate it is by putting two absolute value signs around A. I don't know why it's two. I don't know why it's absolute value signs. That's just the way it is. And that just gives us, so when I do this mathematically, it gives us just the size of A. We don't care about the direction at all, just the size. So I'm going to put them here around our guys. And we have knowns. So sine of 50, we could plug into a calculator. The magnitude of A, we have written up here. Whoops, I want to draw. Up here, 3 meters, just the 3. So we can solve for AY, right? And do really simple algebra. The magnitude of A sub Y is going to be magnitude of A times sine of 50 degrees. And magnitude of A is 3. So I'm going to get out my calculator because I can't do sine in my head. I mean, I guess I technically could, but it would take about an hour for me to do it. There's a Taylor series expansion of sine that's kind of ugly, and I never liked Taylor expansions anyway. Thankfully, we all have calculators, and we don't need to do Taylor expansions anymore. Good, thank God. And you want to make sure that your calculator is in degree mode, because we're using degrees today. Hold on, I just knocked my headphones off. Eventually, we're going to use radians mode, but not today and not in this unit. It's going to take a while. Depending on what kind of calculator you have, for this one, there's a mode button right there. You can see it. It'll get you to this, and you want to just scroll down to radians degrees, hit enter on degrees, and then quit out of it to your main screen. If you're using the phone calculator I suggested, it's a similar thing. I gotta find the dang thing first. Here it is. My phone calculator here. There is a little button on the left side that says trig. Third one down on the left side. Right there. Brings you to this list of trig stuff. At the very top, it has, mine says angles radians, so I'm going to change it to degrees. Just like that, very, very, very top of that screen there. And then I'll select what trig function I want. It was sine. And I'm going to type in 50. 50. And I get sine of 50 is 0.766, blah, 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 blah. If I do the same thing here, sine of 50 on my big calculator, I get the same number. What a coincidence. Amazing. We're so lucky. Yes. So, two ways to do it. If you have a different kind of calculator, I'm sure you have the same controls available. It's just going to be a bit different. And then I'm going to do 3 times that number to get how long my my dude is, a sub y. So if I'm going to, so here I'm going to just write it down. A sub y, the length that we found, is 2.298. 298.1333329, whatever. In this class, I usually just go to 2 or 3 decimal places. I ask you, just 2 or 3 is almost always correct, unless we're doing really, really precise calculations, which happens very rarely, sometimes. But yeah, if you ever have a question, you almost can't go wrong with 2 or 3 decimal places. I guess from a physical perspective, like actually measuring it, if you're measuring meters with like a meter stick, say, 2.298 meters. You're measuring down to the millimeter at that point, which is going to be pretty hard to do with a big old meter stick. So you're not trying to claim, you have nanometer precision by using 8 or 10 decimal places. One of the quickest ways to annoy me is by writing out, all 8 or 12 decimal places that your calculator gives you. Just chop it off or round it at 2 or 3. So, okay, we found out how big a sub y is. This leg is 2.298 meters. We can do something similar for a sub x. I'll do it over here. Can anyone guess what this is going to be without going through this whole process? A sub x is going to be, 3 is the magnitude of a times what trig function? Someone who hasn't spoken up, maybe? I have a little 20-sided dice here that I can use to randomize who I call upon. Although I don't really want to do that. Yeah, it's cosine. Cosine of 50 degrees. Again, I'm going to plug that exact thing into my calculator. 3 times cosine 50, making sure that I'm still in degrees mode, which I am. And I get the a sub x is, I gotta put the absolute values, 1.928 meters. I want everyone to notice that if I add ax, the magnitudes of ax and ay together, it's going to be greater than 3, right? Which is another example to us that we can't just straight up add these two. There's the angle in between them makes a difference. Yeah. But if you do your right triangle like a squared plus b squared equals c squared with these two numbers, you ought to get pretty damn close to 3. In fact, if I use the unrounded version in my calculator, I ought to get exactly 3, or so close that it doesn't make much of a difference. I'll actually do that. Square root. I get 3. Look at me. 3. It's probably backwards on your screen, right? Maybe not. Hooray, 3. Such a good number. Okay. So we figured out ax and ay. I have not left myself enough space to do the rest of this calculation, have I? Could someone, you know what? Could I get help from Chloe? I'm just going to pick someone at random. Chloe, sorry to call you out. Could you just write down those two numbers, ax and ay, and just read them back to me when I need in just half a minute? Because I'm going to start a new page. At the top of this new page, I'm going to say vector A was 3 meters at 50 degrees. Vector B was 2 meters at, what did we say, 130, I think was what I said. Okay, Chloe, could you help me out? What was AX and AY? And AY, let me give me a second to write down, sorry. 2.2, what was it again?
2.29.
Awesome, 298. Thank you so much. I appreciate it. Okay, we're going to do the same thing for vector B. Little buzzy B. Let's see, he looks like this. Let's say there's our B. I always like to draw pictures when I'm doing a physics problem because it really helps me to visualize what's going on. So I'm going to say, I will tell you this a million times, but the first step in doing any good physics problem is drawing a picture, as long as it makes sense. Some of them you probably don't need to. Some of them you're probably fine, but I really like to start by drawing a picture because it really helps ground me in what I'm thinking. I guess the way I do physics problems is trying to run the problem through my head first, as a little experiment, and see what I think is going to happen, and then that kind of informs how I do the math and all that stuff. So drawing the picture first really helps it set in my mind, and I really suggest you guys do it because I think it's a good idea. Okay, and here's the angle we measured was 130 around this way. That's a problem because that angle is not interior to the triangle. What we really want is a triangle like this. Oh god, it's kind of a bad triangle. Triangle with like 5 edges. And we really want like this angle here, right? So how do we find that little interior angle from knowing the exterior angle? Anyone have an idea? Someone who hasn't spoken up yet? I've heard from Elliot, I've heard from Chloe, I've heard from Aiden. Anyone want to give me a volunteer as tribute?
Definitely Levi.
Who was that said that?
Aiden.
Oh, okay. So a rule in my class is that if you volunteer someone else, you get to go. So, Aiden, although you've already gone, could you help us out? How do you get this interior angle by knowing that the exterior angle is 130?
Well, then you add 130 to 90, and since, well, all triangles angles add up, right, to 180.
That's true. All triangles angles add up to 180. So just to remind ourselves, this is essentially the scenario we have. We've measured this as 130, and we want to get this.
Oh, well, then you subtract.
Sorry, I think it's not 130. Isn't it's got to be bigger than one? Isn't it 230?
Yeah, you said it was 300. I thought
It was 300. You're absolutely right. It's 300. Oh my god, 300. Yes, you're right.
So then that's 60.
Yeah, so it's all the way around 360, the entire thing, minus this bit, the 300. So, which is a pretty easy math to do. It's just 60 degrees. And this is, of course, going to be a 30, 60, 90 triangle. Hey, it's almost like I planned it that way. I didn't. Okay, so my interior angle then is 60 degrees. So we can do our sine of 60. I'm going to put parentheses around it just to remind myself. And cosine of 60. Sine is going to be opposite over hypotenuse, so by over b. I'm sorry, the magnitudes of them, I should say. I am getting sloppy and dropping my notation. I will probably eventually do that for good at some point in this class. But for now, I'm going to try to keep good. And then cosine is going to be adjacent over hypotenuse, so bx over b. And this is not so bad, right? So we know the magnitude of b was 2. So 2 times sine 60. And gosh, I'm really hoping that people are following my algebra. I know that this step is really confusing for some students. I am just multiplying both sides by, b here is equal to 2. I'm just multiplying both sides by 2. So 2 times this cancels out here. And 2 cosine 60 Okay, and we can plug these into our calculators. I will do so post haste. 2 sine 60 is 1.732 meters. Always remember to put your units there. I should say a standard thing on my homeworks is if you or anything, homework, test, quiz, whatever, if you forget a unit in your answer, it's off. It's a half a point off. No matter what. So please don't forget. And 2 times cosine of 60 is just 1. That's nice. I genuinely did not plan this way. I just kind of picked some random numbers. Okay. So those are our components. We need to be a little bit careful, though, because I want you to note bx is going in this direction along the positive x-axis, but by is not going along the positive y-axis like ay was. It was going up. By is going down along the negative y-axis, which means it's actually going negative. So the length here, the length here of by is going to be a negative number. I guess this is the absolute value of it. But by, we need to add the negative here because we know the y component of vector b goes down into that fourth quadrant, right? So if we're going to add ax plus bx, it's pretty simple because they're both going in the same direction, both on the positive x-axis. 1.928 plus 1 point, or just 1, so 2.928. Not so bad, but ay and by, we need to be a little bit more careful because ay goes up and by goes down. So it's like by is taking away from ay. So 2.298 minus 1.732. And I'm going to actually write that out. And this minus, again, I'm just going to re-emphasize it, is just because b sub y is going down in the negative y direction. And that is going to be equal to 0.5, I can't write right now, 0.566 meters. So what we've got is the components of our c vector. So we've made a new triangle, which has a big component in x, the cx, 2.298, and a little component in y. Whoops, I have done this totally backwards. Heh. There's y. It's important to get it in the right orientation. I do see students a lot do it the wrong way around. Okay, here's my x and y axis. That's what I need to orient myself. Okay, and so vector c is like there. Oh god, I drew it completely backwards, you guys. We're almost out of time. I'm going to scribble this out. I drew it completely backwards. Even I'm getting tired. Look at this. So there, cx is our big boy. He's 2. And then cy is our little guy. And then our vector c result here. Okay. So really last thing, oh god, we don't have any time left. I really want to finish this though. Our angle, I'm going to call it question mark for now. To get the length of c, I'm going to go through this really fast. I'm sorry, we're going to go through it again. Don't worry. We need to do a squared plus b squared equals c squared. The Pythagorean theorem, right? So cx squared plus cy squared, and then square root of that is going to give us the length of c. I'm going to go so fast. Oh, I'm sorry, guys. This is going to be really confusing. I'm going to do my best to re-explain it next time. So the length of c was 3.320 meters. And the angle it's going at is going to be, so the tangent of our question mark is going to be cy over cx. And I'm hoping you guys know about inverse trig. So tan inverse of cy over cx is going to be equal to our question mark of an angle there. Okay, really quickly. cy, where was it? 0.566 divided by 2.928. And then inverse tangent. So the angle that we get is 10.940 degrees. Okay. Whew, that was a very quick ending. Don't worry if that was super confusing. I know it was. We're going to go back over it next class. I just wanted to finish it before we ended. Thank you guys so much. I will see you on Monday. Any last questions? Awesome. Awesome. It was a lot to get through, you guys. Good job.
Bye.